Looking at this graph of f of x, we can see that A, B, C and D all have something in common. The gradient of the tangent at each of these points is equal to 0. We just draw that on. So the gradient of the tangent at each of these points is 0. That is, the tangent is parallel to the x-axis. Now these points on the graph have a name. They're called stationary points, and there are different types. Here at point A we have a maximum point, at point C we have a minimum point, and at B and D we have what's called a point of inflection. Let's look at this in more detail. Let's zoom into each point. We'll take point A, so we've got this shape, and we'll just mark on point A there. Now before we get to this stationary point where the gradient of the tangent is 0, the function is increasing. Let's write that on there. And when it gets to that stationary point at A, the gradient of the tangent is 0. It's horizontal, the tangent there, parallel to the x-axis. And then after that point, the function is decreasing. This means that once we've determined where this stationary point is, we can identify whether it's a maximum, a minimum, or a point of inflection by considering the gradient before and after that point, the gradient of the tangent. So in this case, for point A, it's a maximum, so the gradient, which is given by the gradient function, will be greater than 0, approaching that point from the left-hand side. At that point, the gradient is 0, and then after that point, the gradient given by the gradient function dy by dx is less than 0. If we take point C, we've got that shape. We'll mark it on. There it is. And again, before point C, the gradient is going to be less than 0 because it's a decreasing function. At point C, the gradient of the tangent is 0, and then afterwards we've got an increasing function. So the gradient of the tangent before, we can write dy by dx. So the gradient of the tangent is given by the gradient function, and at any point before this point C, it's going to be less than 0. And then afterwards, dy by dx is going to be greater than 0. So that's a maximum, that's a minimum. Let's look at point B. So point B, it was coming down like this, and then it was like this. And there's B there. Now this is a point of inflection. So the function in the case of point B is decreasing before it gets to point B. Then the gradient of the tangent at B is 0. And then it's decreasing, that is, the function's decreasing again after that point. So once we've identified that point, before the point, we've got dy by dx, the gradient function is less than 0. At that point, at some point in between here and there, the point B, the gradient is 0. And then afterwards, we've got dy by dx continues to be less than 0 because it's decreasing. And very similarly in the last point, point D, it's coming up like this. Let's mark that on. D, again, just zooming in a little bit. We've got the gradient at point D is 0. And before, as we're approaching D from the left-hand side, the function is increasing. At point D, the gradient of the function is 0, and then thereafter it's again increasing. So once we've found point D, we've located it, we can decide what type of stationary point it is by looking either side of this point. And the gradient as it approaches D is greater than 0. Then at Z it's 0, at D it's 0, and then after that point it's greater than 0. So we've got 3 different scenarios: a maximum, a minimum, or a point of inflection. Here is an equation of a graph or a function. We've got y equals x cubed minus 3x squared minus 9x plus 10. And we want to find any stationary points that are on this graph and also the nature of those stationary points. And then I think we'll sketch the graph as well. Well, we know that at any stationary point, the gradient of the tangent at that point is 0. So if we find the gradient function, by differentiating this, we get 3x squared minus 6x minus 9. Like we said, we know that the gradient at a stationary point is 0. So we'll let dy by dx equals 0 to find the corresponding values of x, the x coordinates, if you like, of those stationary points. So I've got 3x squared minus 6x minus 9 equals 0, and I want to solve this equation. Well, first of all, I noticed that 3 is a factor here, so if I divide each term by 3, including the 0, I get x squared minus 2x minus 3 equals 0, and I want to factorise this, so I'm going to get x plus 1 and x minus 3 equals 0. So my two solutions, the 2 points, or the x values of the points where the gradient of the tangent to my original function is 0, are x equals minus 1 and x equals 3. But I want to find the coordinates of the points, the stationary points. So when x equals minus 1, if I want to find the y value, I've got to go back to the original function. And if I put minus 1 in here, I've got negative 1 or minus 1 cubed, minus 3 lots of minus 1 squared, minus 9 lots of minus 1, plus 10. And if I put that in the calculator, it'll tell me that it's 15. So there's a stationary point at negative 1, 15. Similarly, if we put 3 in for x, we've got 3 cubed minus 3 lots of 3 squared, minus 9 lots of 3, plus 10. And if I put that into a calculator, it will give me a value of negative 17. So we know this graph has got stationary points at negative 1, 15 and at 3, negative 17. But what are the nature of those stationary points? Well, to do that, I'm going to draw a little table with 3 columns. In the first row is going to be my value of x, and in the second row is going to be the value of the gradient at a specific point given by the x value. Let's go for negative 1 first. Now we know at x equals negative 1 or x equals minus 1, the gradient of the tangent at that point is 0. And we're going to look at either side. So we'll have negative 2 and we'll have 0. So if we put negative 2 into our derivative here, what do we get? We get 3 lots of negative 2 squared, so that's 12, minus 6 times negative 2, which is plus 12, so that's 24. Take away 9 is 15. So this has a positive gradient. This has a gradient of 0. And then let's see what happens when we put 0 into this. 0 minus 0 minus 9 is minus 9. So we can see from this shape we've got an increasing function, then we've got our stationary point, and then a decreasing function. So there is a maximum point, or a maximum stationary point, at x is minus 1, and we worked out earlier that at minus 1 y is 15. Now we do the same thing again for our other value, x equals 3. Now we're going to use x is 3 this time, and we want to go either side of that point to determine the nature of this stationary point. So I'm going to go 2 and I'm going to go 4. Now we know the gradient when x is 3, the gradient of the tangent at that point is 0. But what about when it's 2? So we go back to our derivative. 3 lots of 2 squared is 12, minus 6 lots of 2, so that's 12 minus 12 is 0, minus 9 is minus 9. So we've got a negative gradient, a decreasing function, followed by our stationary point. and then we'll put a 4 into our gradient function. So 3 lots of 4 squared is 48, minus 6 lots of 4, which is 24 there. So 48 minus 24 is 24, and then we minus 9, we get 15. So that's a positive gradient. So we've got a decreasing function to the stationary point to an increasing function. So we've got a minimum at 3, and the corresponding y value for that was negative 17. When it comes to sketching the graph, what I do is draw the maximum minimum points first and then connect those and think about where the x-axis goes. So we know we have a maximum at negative 115. So I'll draw that shape first, put a little cross there and write in negative 115. And then we've got a minimum at 3, negative 17. So I'm going to draw like this, back up there, and put a cross. 3, negative 17. I might extend that a little bit to show that I know what's going on there with the shape. So the x-axis has got to be somewhere between these 2 points, because that's above the x-axis, that's below the x-axis, and it's also closer to this point here. So I grab a ruler, I draw the y-axis, and I draw the x-axis. Now it's only a sketch, isn't it? So it doesn't have to be super duper accurate, but it's good to get the axes in the correct position. So this makes sense because -1 is to the left of the y-axis and 3 is to the right of it. I'm going to mark 0 on, I'm going to label it x and y. And it's important to get the stationary points that we've determined on our graph. I'm also going to label this y equals f of x. Now you might get asked one further question, that is, determine the number of roots of the equation f of x equals 0. Well, f of x equals 0 is to try and solve the equation when y equals 0. That is, how many times does the graph intersect or cross or touch the x-axis. So here we've got 1, 2, 3 roots. So there are 3 roots to this equation.